Hey guys, Mr. Wooten here once again. This is the last problem where you are simply solving expressions for a letter here in this first unit study guide dealing with equations and inequalities. So question number 7 again is asking us to solve for the letter x. And if you look at the equation, we have 5 plus 7x equals 7x minus 12. And if you look at this problem at first, you may look at this and say, well, this looks much easier than the ones we've been doing, like in questions 4, 5, and 6. And you would be correct, it does look easier. But this is a very interesting problem. If we look at this, there's no parentheses, no exponents, no multiplying other than simply the 7 times the x on both sides. So all we need to do is we need to go ahead and just start solving this equation for x. And if you watched previous videos, or if you know this from your background knowledge, you know that to solve an equation that has x's on both sides for the letter x, we need to cancel out the x's on either side. So if I look at this, then if I want to cancel out the x's, I'm just going to pick the left side of the equation. I'm going to subtract 7x, since that was adding 7x, from both sides. Okay, and this is kind of interesting what happens here. Alright, so we have 5 plus 7x, we take away 7x, those cancel, and I'm just left with the 5, equals, and then here on the right hand side, 7x minus 7x, you may think about, well, wait a minute, that also cancels out. Positive 7 minus 7 cancels out, so I'm just left with negative 12. So what's really interesting about this problem is when I subtract the 7x from both sides, they cancel out. There are no x's left in this equation. And you may think, well, I did something wrong. Let me go back. Maybe I was supposed to end up with 14x here or here. But you're not. Okay? This is an interesting problem. And if you look at the result here, we get 5 equals negative 12. So think to yourself, does 5 equal negative 12? The answer is clearly no. This does not work. Okay? So what we come across is a problem, an equation that has no solution. Okay? If you ever are solving a problem and all your x's cancel out, if you've done it correctly, now obviously there are times you can make a simple mistake and accidentally lose your x's when you didn't need to, but if you cancel out the x's on one side and it's the same number of x's on both sides, then you may come across a problem that does in fact have no solution. Okay, now I want to talk about this graphically for a second. I want to talk about what this would look like on a graph. Because if you look at this left-hand expression, 5 plus 7x, what type of function is that? If I was to write a y equals equation out of this, y equals 5 plus 7x, hopefully the first thing that comes to your mind, remember there are 3 big type of functions we've learned this year. Linear, and I'm going to abbreviate some of these, exponential, and quadratic. Okay. Linear functions, we're used to seeing those in y equals mx plus b form, and you may already be able to tell this is kind of like our mx plus a b number plus our y-intercept. Exponentials, those are given away because they have a variable as the exponent, usually, and then we also have quadratics that always have an x squared term in the expression. Okay, so this is in fact a linear expression. Well, if we look at the right-hand side, 7x minus 12, okay, even though the 12 is a negative, that is still a linear function. Okay, mx plus b, it's just our b is a negative number, negative 12. So these are 2 linear expressions. If I was to look at a graph of this, I'm just going to make a sketch of this for you, then we've already seen algebraically that our x's go away and we end up with an equation that does not make sense. 5 does not equal negative 12. And we said that that must mean there is no solution. Well, if I had looked at this graphically, then my y-intercept for this first equation was 5. Okay, so here it is at 5, and then the slope is 7. That means I rise 7 and I run 1. Okay, so I'm going to go up 7 over 1, wherever this would be. And then if I was to try and find another point, I could go backwards 1 and then down 7 to figure out my other point. Okay, and I would be somewhere over here. So that would be one of my lines. Okay, and that was a very sloppily drawn line. Let me try and, having trouble here. Let's try and draw this a little bit straighter. There we go. Okay, and then I'm going to draw this through here. That wasn't perfectly placed point, but you get the idea. So this will be a line 5 plus 7x. Over here, I have a y-intercept of negative 12, so that's going to be way down here somewhere, probably off our screen even. And then it's going to go up 7 and over 1, probably somewhere in there. Then up 7 and over 1 again, probably somewhere in there. And what we're going to end up seeing, if I had drawn these lines correctly, okay, on an actual graph, again, pardon me that these aren't correct as far as the locations, but if you notice, this line has a slope of 7, this line has a slope of 7. And those are going to indicate a special set of lines that are, if you remember, lines with the same slope are parallel. Because if we think about it, they start a certain distance apart. This one starts at a value of positive 5. This starts at a value of negative 12. Okay? So those are a total of, if you were to do the math, 17 units apart. This one's 5 above, this one is 12 below. That's a total of 17 units apart. If I go over one space, this line has gone up a total of 7, according to the slope. This line has gone up a total of 7. Since they both went up the same amount, they did not get any farther apart or any closer. They are still 17 units apart. If I go over one more, this one goes up 7, this one goes up 7. They're not any closer or any farther apart. They are still 17 units away from each other. So those are what we call parallel lines. And if you remember, solving an equation like this is really, where you have x's on both sides, you're really simply finding the intersection of each of those two lines, if you were to look at that graphically. And since these lines will never cross, that in fact means there is no solution to this problem. So we can see that graphically that there is no solution. Those are parallel lines. And then algebraically, this is what you get when you come across a set of parallel lines that you're trying to solve those equations for x. Okay, so you get an equation that does not make sense with a number equal to another number that are in fact not equal to each other. And I want to mention one other thing. Had we looked at this problem, and this is kind of a side note, it's not part of the actual problem. What if this equation right here had originally been 7x plus 5? So if it said 5 plus 7x equals 7x plus 5, I still would have taken away 7x and those would have canceled, but instead of a minus 12, I would have been left with 5 over here. So if I saw 5 equals 5, well, that equation actually does make sense. 5 does equal 5, but again, there are no x's. If you solve an equation, your x's go away, and you're left with two numbers that are not equal, then there is no solution. If you are left with two equations that are equal, two values that are equal, like 5 equal to 5, that is always true. That is an example of a problem that has an infinite number of solutions. Okay? Infinite solutions. And what that would look like on a graph is simply, if you may already notice this, 5 plus 7x, is that really any different than 7x plus 5? And the answer is no. They have the same slope, they have a slope of 7, and the same starting value or y-intercept of 5. So both of those lines would simply lie right over top of each other at 7x plus 5, and that line is always crossing the other line. Okay, it's sitting right on top of it. That is, there is a solution at every single point on that line. If we're saying that a solution is where the lines cross, they always cross each other. They're always connected. So that would be an example of one with infinite solutions. So if you do the math and you come across those, remember, if you end up with no x's but a number equal to another number and it's true, they're always equal to each other, 5 always equals 5, then it's infinite solutions. If you get a number like 5 equals negative 12, we'll go back to that example, and they're never equal to each other, then that is an example of no solution. Those are parallel lines. Okay? So that is question number 7. Very interesting problem to show you what happens if you come across a problem that either doesn't have a solution or has infinite solutions, where your x or your variable goes away. But just wanted to kind of refresh your memory on how that works. Again, if you have any questions, if you'd like more practice with this, leave a comment, or you can check with me in class or send me an email. Again, I will be happy to give you any more practice problems you would request as you go through these. Just let me know. Keep me updated on where you're at and what your progress looks like. And once you're done with these first 7 problems, feel free to move on to the next set you have questions with.